Cross-validation is a popular method for evaluating the performance of a machine learning model. This technique is frequently employed in practical machine learning applications to compare and select an appropriate model for a given predictive modeling problem. Cross-validation is straightforward to grasp and implement, and it typically produces less biased results than other methods used to assess a model's efficiency scores. As a result, cross-validation serves as a powerful tool for identifying the best model for a particular task. There are a lot of different techniques that may be used to cross-validate a model, such as k-fold, leave one out, leave p out, stratified k-fold, and repeated k-fold. First technique, holdout cross-validation. The holdout technique is an exhaustive cross-validation method that randomly splits the dataset into train and test data depending on data analysis. In the case of holdout cross-validation, the dataset is randomly split into training and validation data. Generally, the split of training data is more than test data. The training data is used to induce the model, and validation data evaluates the performance of the model. The more data is used to train the model, the better the model is. For the holdout cross-validation method, a good amount of data is isolated from training. It is really easy to implement holdout. For example, you may do it using sklearn. Model selection, train test split, not suitable for an imbalanced dataset. A lot of data is isolated from training the model. K-fold cross-validation is a technique that minimizes the disadvantages of the holdout method. K-fold introduces a new way of splitting the dataset, which helps to overcome the test only once bottleneck. The algorithm of the K-fold technique step. Step 1. Pick a number of folds, k. Usually, k is 5 or 10, but you can choose any number which is less than the dataset's length. Step 2. Split the dataset into k equal parts. Step 3. Choose k1 folds as the training set. The remaining fold will be the test set. Step 4. Train the model on the training set. On each iteration of cross-validation, you must train a new model independently of the model trained on the previous iteration. Step 5. Validate on the test set. Step 6. Save the result of the validation. Step 7. Repeat steps 3, 6k times. Each time use the remaining fold as the test set. In the end, you should have validated the model on every fold that you have. Step 8. To get the final score, average the results that you got on step 6. In general, it is always better to use k-fold technique instead of holdout. In a head-to-head comparison, k-fold gives a more stable and trustworthy result since training and testing is performed on several different parts of the dataset. Still, k-fold method has a disadvantage. Increasing k results in training more models, and the training process might be really expensive and time-consuming. To perform k-fold cross-validation, you can use sklearn. Model selection, k-fold. Leave one out. SROS validation is an extreme case of k-fold CV. Imagine if k is equal to n, where n is the number of samples in the dataset. Such k-fold case is equivalent to leave one out technique. The algorithm of leave one out technique steps. Step 1. Choose one sample from the dataset, which will be the test set. Step 2. The remaining n1 samples will be the training set. Step 3. Train the model on the training set. On each iteration, a new model must be trained. Step 4. Validate on the test set. Step 5. Save the result of the validation. Step 6. Repeat steps 1, 5 n times, as for n samples we have n different training and test sets. Step 7. To get the final score, average the results that you got on step 5. To perform k-fold cross-validation, you can use sklearn. Model selection, leave one out. The greatest advantage of leave one out cross-validation is that it doesn't waste much data. We use only one sample from the whole dataset as a test set, whereas the rest is the training set. But when compared with k-fold CV, leave one out requires building n models instead of k models, when we know that n, which stands for the number of samples in the dataset, is much higher than k. It means leave one out is more computationally expensive than k-fold. It may take plenty of time to cross-validate the model using leave one out. Leave p out cross-validation is similar to leave one out, as it creates all the possible training and test sets by using p samples as the test set. All mentioned about leave one out is true and for leave p out. Still, it is worth mentioning that unlike leave one out and k-fold, test sets will overlap for leave p out if p is higher than 1. The algorithm of leave p out technique steps. Step 1. Choose p samples from the dataset, which will be the test set. Step 2. The remaining n p samples will be the training set. Step 3. Train the model on the training set. On each iteration, a new model must be trained. Step 4. Validate on the test set. Step 5. Save the result of the validation. Step 6. Repeat steps 2, 5 CPN times. Step 7. To get the final score, average the results that you got on step 5. Leave p out has all the disadvantages of the leave one out, but nevertheless, it's as robust as leave one out. Sometimes we may face a large imbalance of the target value in the dataset. Stratified K-fold is a variation of the standard K-fold CV technique, which is designed to be effective in such cases of target imbalance. It works as follows. Stratified K-fold splits the dataset on K-folds such that each fold contains approximately the same percentage of samples of each target class as the complete set. In the case of regression, stratified K-fold makes sure that the mean target value is approximately equal in all the folds. The algorithm of stratified K-fold technique steps. Step 1. Pick a number of folds, K. Step 2. Split the dataset into K-folds. Each fold must contain approximately the same percentage of samples of each target class as the complete set. Step 3. Choose K1 folds, which will be the training set. The remaining fold will be the test set. Step 4. Train the model on the training set. On each iteration, a new model must be trained. Step 5. Validate on the test set. Step 6. Save the result of the validation. Step 7. Repeat steps 3, 6K times. Each time use the remaining fold as the test set. In the end, you should have validated the model on every fold that you have. Step 8. To get the final score, average the results that you got on step 6. As you may have noticed, the algorithm for stratified K-fold technique is similar to the standard K-folds. You don't need to code something additionally, as the method will do everything necessary for you. Stratified K-fold also has a built-in method in Sklearn. Model selection. Stratified K-fold. All mentioned above about K-fold CV is true for stratified K-fold technique. When choosing between different CV methods, make sure you are using the proper one. For example, you might think that your model performs badly simply because you are using K-fold CV to validate the model which was trained on the dataset with a class imbalance. To avoid that, you should always do a proper exploratory data analysis on your data. Repeated K-fold cross-validation is probably the most robust of all cross-validation techniques. It is a variation of K-fold, but in the case of repeated K-folds, K is not the number of folds. It is the number of times we will train the model. The general idea is that on every iteration we will randomly select samples all over the dataset as our test set. The algorithm of repeated K-fold technique steps. Step 1. Pick K, number of times the model will be trained. Step 2. Pick a number of samples which will be the test set. Step 3. Split the dataset. Step 4. Train on the training set. On each iteration of cross-validation, a new model must be trained. Step 5. Validate on the test set. Step 6. Save the result of the validation. Step 7. Repeat steps 3-6K times. Step 8. To get the final score, average the results that you got on step 6. Sklearn will help you to implement a repeated K-fold CV. Just use Sklearn. Model selection. Repeated K-fold. In Sklearn implementation of this technique, you must set the number of folds that you want to have and the number of times the split will be performed. It guarantees that you will have different folds on each iteration. Repeated K-fold has clear advantages over standard K-fold CV. Firstly, the proportion of train-test split is not dependent on the number of iterations. Secondly, we can even set unique proportions for every iteration. Thirdly, random selection of samples from the dataset makes repeated K-fold even more robust to selection bias. Still, there are some disadvantages. K-fold guarantees that the model will be tested on all samples, whereas repeated K-fold is based on randomization, which means that some samples may never be selected to be in the test set at all. At the same time, some samples might be selected multiple times, thus making it a bad choice for imbalanced datasets. When is cross-validation the right choice? Although doing cross-validation of your trained model can never be termed as a bad choice, there are certain scenarios in which cross-validation becomes an absolute necessity. 1. Limited dataset. Let's say we have 100 data points and we are dealing with a multi-class classification problem with 10 classes. This averages out to 10 examples per class. The smart thing to do here would be to use cross-validation and utilize our entire dataset for training as well as testing. 2. Dependent data points. When we perform a random train-test split of our data, we assume that our examples are independent. It means that knowing some instances will not help us understand other instances. However, that's not always the case, and in such situations, it's important that our model gets familiar with the entire dataset, which is possible with cross-validation. 3. Cons of single metric. In the absence of cross-validation, we only get a single value of accuracy, or precision or recall, which could be an outcome of chance. When we train multiple models, we eliminate such possibilities and get a metric per model, which results in robust insights. 4. Hyperparameter tuning. Although there are many methods to tune the hyperparameters of your model, such as grid search, Bayesian optimization, etc., this exercise can't be done on training or test set, and a need for a validation set arises. Thus, we fall back to the same splitting problem that we have discussed above, and cross-validation can help us out of this.